Maritime Academy.
Corrosion and its prevention. Aims. Understands corrosion and its prevention. Objectives. Describes the various corrosion processes. Describes the painting systems used on ships. Describe cathodic protection systems on vessels. Natural tendency of all metals is to react with their environment. The result is corrosion equals substance of very similar chemical composition to the original mineral. When man produces iron to build a ship, he is taking a relatively stable substance, iron ore, and purifying it until it becomes an unstable substance. So unstable in fact that it wants to decompose in the presence of oxygen. Metal plus damp atmosphere equal oxide. If insoluble equal protective layer plus prevents any further corrosion, e.g. copper and aluminium. Oxide, soluble equal oxidation continues equal corrosion and erosion, e.g. iron. Corrosion is the wasting of metals by chemical or electrochemical reactions with the environment. Erosion is the destruction of a metal by abrasion, thus it is a mechanical wastage process that exposes bare metal which can then corrode. Atmospheric corrosion may occur during shipbuilding when RH is greater than 70%. Its rate depends on air pollution by smoke and/or salt. Chemical corrosion. Chemical reaction. Atmospheric corrosion. Oxidizing. Superstructure main deck, boot top area. Electrochemical corrosion. Electrochemical reaction. Galvanic or corrosion cell. Anode and cathode. Immersed area. Ship's bottom area. Bimetallic corrosion. Galvanic corrosion. Two different metal, iron and aluminum connection. Erosion. Impingement attack, air bubbles, cavitations, collapse or implode. Pipelines. Immersed area of hull. Stress corrosion. Inherent or due to working in the seaway. Cold flange brackets, welded joints. Pitting corrosion. Localized spot and perforation of metal. Superstructure and main deck. Microbiological corrosion. Deterioration. Bacteria, algae, molds, fungi, ballast and fuel tanks. Crevice corrosion. Narrow openings or spaces between two metal surface or metal and non-metal surface, flanges, washer. Deposit corrosion. Under or around a discontinuous deposit on a metallic surface. Oxygen concentration cell. Corrosion and its prevention. Chemical corrosion is the oxidizing or rusting of iron/steel by chemical reaction. When exposed to oxygen and moisture, primarily, it can be prevented by isolating it from the environment. Ship's bottom area, completely. Boot topping area, intermittently, are immersed in seawater, ideal condition for formation of electrochemical corrosion cell. Thus need a great deal of care to prevent excessive corrosion. Electrochemical corrosion is the oxidizing or rusting of unprotected iron/steel by electrochemical reaction when submerged in seawater. Primarily a corrosion cell or is formed between two metal surfaces, not necessarily different metals, in a solution of salt water, the electrolyte. When connected externally, a current will flow from one metal, the anode, to the other, the cathode, as a result of a potential difference between them. This current flow results in metal being removed from the anode whilst the cathode is protected. The galvanic cell. Galvanic series. Common shipbuilding metals may be arranged to show relatively which one would become an anode or cathode when placed in seawater. Passive stainless steel, bronze, copper, brass, active nickel/nickel alloys, mill scale, active stainless steel, cast iron, iron/steel, aluminium, zinc, magnesium. Galvanic series. Metals of the world are arranged in series. Those on top are considered cathodic, noble. Those at the bottom are anodic, ignoble. If any two metals are connected externally in an electrolyte, the metal at the lower end of the series will waste. To protect steel using the sacrificial anode system, metals that are anodic to steel are welded to the steel hull so that these waste, e.g., Ng and Zn. The corrosion cell. Steel plate is not perfectly homogeneous and will therefore have anodic and cathodic areas. Corrosion may therefore occur when such a plate is immersed in an electrolyte such as seawater or even exposed to air and moisture. The majority of the corrosion of ships is due to this electrolytic process. Bimetallic corrosion, name given to corrosion occurring when two different metals form part of a corrosion cell. Galvanic corrosion, the metal which is relatively lower or less noble in the galvanic series will form the anode, tend to corrode, whilst the one which is relatively higher or more noble will form the cathode and be protected. There are many possibilities of such cells forming on board. Aluminum and steel in close proximity in the presence of water. Erosion, essentially it is the loss of metal due to mechanical action. However, it may become associated with electrochemical corrosion under certain circumstances, namely, impingement attack. Air bubbles entrained in flow of water strike metal surface on the hull and erode any protective film. Eroded surface becomes anode to the surrounding surface and corrosion occurs. Corrosion cell. This effect is greater if the water is warm. Locations in way of ship's seawater discharges. Cavitations. At certain regions in the flow, the local pressures drop below that of the absolute vapor pressure. Vapor cavities, that is areas of partial vacuum, are formed locally. But when the pressure increases clear of this region, the vapor cavities collapse or implode. This collapse occurs with the release of considerable energy, and if it occurs adjacent to a metal surface, damage results. The damage shows itself as pitting, which is thought to be predominantly due to the effects of the mechanical damage. Corrosion due to metal stress. Accelerated corrosion may occur in locations where the metal is stressed, either inherent or due to working in the seaway, leading to fatigue and minute cracks, with corrosion cells forming at these cracks. The combined action of stress and the consequent corrosion may have a considerable effect on the metal. Places liable to such localized corrosion are cold flanged brackets, welded joints, aluminum/magnesium alloy rivets. Pitting corrosion. Corrosion at one spot so localized that eat away the spot and finally perforate the metal. Microbiological corrosion. Deterioration of material caused directly or indirectly by bacteria, algae, molds, fungi single or in combination. Crevice corrosion is a localized form of corrosive attack. It occurs at narrow openings or spaces between two metal surface or between metal and non-metal surface. A concentration cell forms with the crevice being depleted of oxygen. This differential aeration between the crevice and external surface gives the crevice an anodic character, e.g. flanges, washer, threaded joints, gaskets, O-rings. How to reduce it? 1. Eliminate the crevice from the design. 2. Select materials more resistant to crevice corrosion. 3. Reduce the aggressiveness of the environment. Deposit corrosion. The corrosion occurring under or around a discontinuous deposit on a metallic surface. It is due to attack as a result of an oxygen concentration cell set up under deposits of organic matter. It is also called poultice corrosion. Control of corrosion on board can be 1. The application of barrier or protective coating to isolate the steel or other metal from the air or from the seawater electrolyte, e.g. paint. 2. Using cathodic protection to prevent the steel from forming the anode of a corrosion cell, sacrificial zinc anodes, or impressed current systems. This can be used only in submerged areas, like the ship's underwater hull or in ballast tanks. It may be quite common on modern ships to find both the control methods being used to complement each other. Paints is a mixture of three elements, namely, the pigment provides color and covering capacity, includes any special additives. The vehicle or binder decides consistency, adhesion, ease of application, and film quality. The solvent or thinner added to dissolve the vehicle, making the paint flow easily and control drying time. Drying process. 1. When the vehicle consists of solid resinous material dissolved in a volatile solvent, the latter evaporates after application of the paint, leaving a dry film. 2. A liquid like linseed oil as a constituent of the vehicle may produce a dry paint film by reacting chemically with the surrounding air. 3. A chemical reaction may occur between the constituents of the vehicle after application to produce a dry paint film. The reactive ingredients may be separated in 2 containers, 2 pack paints, and mixed before application. Painting systems. An appropriate solvent is essential to ensure proper drying time, e.g., if drying is too quick, blistering may occur. Common vehicles used in corrosion-inhibiting paints include 1. Bituminous or pitch, bitumen/pitch dissolved in a white spirit solvent. 2. Oil-based, vegetable drying oils like linseed oil, dehydrated castor oil, not suitable for underwater area. 3. Oleoresinous, natural or artificial resins mixed into drying oils. 4. Alkyd resin, a special oleo resin, not suitable underwater. 5. Chemical resistant, extremely good resistance to severe condition of exposure. Chlorinated rubber. Epoxy resins, coal tar/epoxy resin, polyurethane resins, vinyl resins, polyurethane not suitable underwater. 5. Chemical resistant vehicle. 5.1 Epoxy resins, produced from petroleum, natural gas, very good adhesion and excellent chemical resistance, good flexibility and toughness. 2 packs and expensive. 5.2 Coal tar/epoxy resin, similar to above, but a grade of coal tar pitch is blended with the resin. A formulation of this type combines to some extent the chemical resistance of the epoxy resin with the impermeability of coal tar. 5.3 Chlorinated rubber, consists of a solution of plasticized chlorinated rubber, or isomerized rubber. Isomerized rubber is produced chemically from natural rubber, and it has the same chemical composition but a different molecular structure, thick film and resistance to attack from acid and alkalis. 5.4 Polyurethane resins, 1/2 pack paint is available. Properties are toughness, hardness, gloss, abrasion resistance, as well as chemical and weather resistance. It is not used in underwater area, only used on superstructure. 5.5 Vinyl resins, obtained by the polymerization of organic compounds containing the vinyl group. Solid content is low, thus dry film is thin and require more coats. Poor adhesion to bare steel, so generally applied over pretreatment primer. It is effective for UW protection of steel. Painting systems. Antifouling paints. Fouling is the covering up of ship's bottom by green slime, weeds, and barnacles. Fouling increases when ship is at rest for long periods or has a slow speed. Some organisms can grow at speeds up to 10 knots. AF paint consists of vehicle with pigments and toxic materials, e.g., copper. AF paints works by slowly releasing or leaching poison into the sea layers, destroying the fouling-causing organisms. Tributyl tint TBT-based antifouling paint, most common in the past, have been banned for use since January 1, 2003 as they used to damage to the shellfish and marine environment. IMO deadline 2008. Painting systems. Antifouling paints. To prolong the useful life of the paint, the toxic compounds must dissolve slowly in seawater. Once the release rate falls below a level necessary to prevent settlement of marine organisms, the antifouling composition is no longer effective. The effective period for traditional compositions was about 12 months. To reduce very high docking costs, an AFP developed with an effective life up to 24 months in the early 1970s. Self-polishing AFP with longer effective life, 5 years, and smooth surface, which reduces friction and fuel consumption, was developed. Corrosion and its prevention. Currently, TBT-free antifouling paints may be of 2 types. Biocidal, where a chemical or biocide, usually copper oxide, is leached into the seawater layer at a controlled rate to inhibit the growth of fouling organisms for periods ranging from 24 months for self-polishing paints using rosin-based binders to 16 months for self-polishing paints using acrylic polymer-based binders. Foul release, where a silicone-based non-stick surface does not allow fouling organisms to adhere to it. To be effective, ship is required to have speeds greater than 30 kds in coastal waters and over 15 kds deep sea. Coating is easily damaged by abrasion and needs regular cleaning. This type is not very commonly used currently. Mill scale, resistant iron oxide, FeO, scale formed on steel during hot working processes in REG, during hot rolling, heat treatment, hot fabrication, etc., may appear like a shiny bluish film on new steel, can be removed by weathering. use of mild acids, sandblasting, etc. The most effective method of removing mill scale is shot blasting. This system removes 95% to 100% of mill scale, surface rust, dirt, etc., and results rough surface for adequate adhesion of the paint. Surface preparation for painting includes removal of mill scale from new plates, set up corrosion cell and cause paint film to be removed, removal of rust and damaged paint from existing plates, ensuring surfaces are clean, free of grease/oils, and dry. Modern paints, such as epoxy and polyurethane, require very clean shot-blasted surface. In shipyards, steel is given temporary protection during shipbuilding by use of a holding or shop primer, usually low zinc-based. It has the following properties: 1. Non-toxic and dries rapidly. 2. Does not give fumes during welding/cutting. 3. Is compatible with other paints. The most common methods employed to prepare steel surfaces for painting are: blast cleaning is the most efficient method for preparing the surface. Pickling, immersion of the metal in an acid solution, usually hydrochloric or sulfuric acid, in order to remove the mill scale and rust from the surface. Flame cleaning, useful for cleaning plates under inclement weather conditions, the flame drying out the plate. Preparation by hand, by various forms of wire brush, is often not very satisfactory and would only be used where the mill scale has been loosened by weathering, i.e., exposure to atmosphere over a long period. Protection by paint, prevent attack on the metal covered simply by excluding the corrosive agency. The paint is richly pigmented with a metal anodic to the basis metal like zinc dust as sacrificial anode with respect to the steel. Protect by certain pigments, red lead, zinc chromate, anodic or cathodic inhibitor. Protection against marine vegetables/animal to grow on UW area by antifouling paint. Summary of ships painting systems. Cathodic protection systems. This method can be used to protect ship's steel from corrosion when the steel is immersed in water. Electrolyte. It prevents the steel from forming the anode of a corrosion cell and operates by providing a reverse current flow to that of the normal corrosion cell. A protection current of about 12 to 100 mA/SQ meter is provided when the potential of the immersed hull is about 0.8 volt more negative than a reference silver electrode nearby. It must be considered to supplement painting systems, not as a substitute. Two types of methods are available: the sacrificial anode system, the impress current system. The sacrificial anode system. Metals or alloys that are less noble than ship's steel are used as anodes, usually aluminum, magnesium, or zinc alloys. The anode is welded to the hull by their steel cores to give a good electrical connection. The anode supplies a protection current of about 12 to 20 mA/SQ meter and is sacrificed in the process. The lifespan of sacrificial anodes is around 2 to 4 years, depending on paint conditions. Note: ballast or cargo/ballast tanks are also protected by sacrificial nodes. Magnesium anodes are not used owing to the spark hazard. Aluminum anode systems may be employed in tankers, provided they are only fitted in locations where the potential energy is less than 28 kilograms. Sacrificial anode. Corrosion and its prevention. The impress current system. Appropriate voltage difference is maintained between the steel hull and fitted non-consumable anodes, who are provided with a DC current rectified from the ship's AC supply. Reference electrodes of silver form a reference cell which detects the potential difference between the steel hull and itself, and a controller compares this current against a preset protective value. In case of variation, the controller signal activates a reactor to suitably provide the DC current to the anodes, lead/silver, platinum/palladium. The impress current system. Typical feature: longer intervals between dry dockings, reducing operating costs, minimum time and cost for maintenance, fully automatic operating giving optimum hull protection, better long-term hull protection than Sacrificial anode system, minimum frictional resistance on the hull, constant hull potential monitoring for continuous protection, smaller and lighter than any other anode. Enhanced structural protection. This is a painting system suggested for use in tankers and bulk carriers to prolong their life at sea. The painting system is so developed such that key areas, vessels' decks, cargo tanks, water ballast tanks, underwater hull and top sides of a vessel can survive uninterrupted service periods without the paint coats being damaged for periods of up to 20 years. Requirements before paint application: 1. Good pretreatment standards. 2. Controlled conditions while painting. 3. Advanced technology. 4. Experienced supervisors. Where aluminum superstructures are introduced, the attachment to the steel hull and the fitting of steel equipment to the superstructure require special attention. This latter problem is overcome by insulating the two metals and preventing the ingress of water as illustrated in Figure 27.2. A further development is the use of explosion-bonded aluminum/steel transition joints, also illustrated. These joints are free of any crevices, the exposed aluminum to steel interface being readily protected by paint. Corrosion and its prevention by good design. Discharges or scuppers must be designed not result dripping water. Proper ventilation should be arranged for underside of enclosed structure to avoid condensation of moisture. Steel decks, which covered by wood, can be corroded unless it is suitably protected and the wood is scaled by bitumen coating. All joints must be sealed by suitable filler, and any bolt through the woods should have proper washers under nut. Surface of metals to be covered by adequate thickness of paint. Welding can be used to fill small cracks. Welded surface to be suitably prepared for painting. Proper paint to be applied in places where the machinery sets must be fitted. Where the aluminum superstructure is in contact with steel deck transition plate shall be used. Two different metals in contact in the presence of an electrolyte can result corrosion cell. Proper insulation must be made. The atmosphere of V/R is in contact with the heat, moisture, vibration, which can result corrosion. The surfaces should be kept water-free by good drainage design, insulation of steam pipes, and proper ventilation to avoid condensation. Sharp bend to be avoided in piping system. To avoid erosion, questions. Describe the impressed current system. Explain your understanding of the term enhanced structural protection. Describe with the aid of a diagram a typical ship's painting scheme. Explain your understanding of self-polishing paints and TBTs. Explain your understanding of the following: corrosion by erosion, stress corrosion, and galvanic corrosion. State your understanding of the term galvanic series. Explain briefly the properties of a paint.
Maritime Academy.